Hi, and welcome to today's episode. In this video, I'm going to be discussing functions and relations and how they differ from one another. So let's start off with the definition. All functions are in fact relations, but not all relations are functions. The difference between a relation and a function is that in a relation, you can have many outputs for a single input. However, in a function, a single input only has a single output. So let's dive into this and examine different forms of function representation and assess whether it's a function or a relation. Let's start off with sets. In set A, we have four different coordinates, and these examples, our first number would correspond to our x coordinate, and the second number would correspond to the y coordinate. And in all of our examples, x is our independent value or variable, depending on which form of function we're examining, and y would be our dependent value or variable. Just wanted to put that out there. So in this in this example, we know that the first numbers represent some input value x, so 3, 22, 41, and 1. And based on the definition of a function, which says that a single input should have only a single output, then we could assess whether that is the case. We know that all of these input values are different and they only have one output per each single input. Therefore, set A does represent a function. Does represent a function. Now, I'm going to move this a little further down. Now, for set B, we have 1, 18, 33, and 1 again. So we have 1 here, 1 here. So our input value 1 has two outputs. One is 11 and the other is 101. And based on the definition of a function, which says that a single input has a single output, this is in violation of that definition. Therefore, set B does not represent a function. Now, functions can also be represented through mapping diagrams. And the examples you see on the screen, this represents our x or input value, and this side represents our y or output value. And in the first example, we could see that the input value 3 results in output value 8. Input value 4 results in output value 1. 16 results in 12, and 11 results in 9. Each input value has one unique output value, does not have two different output values, therefore this is a function. Now, on this side, the second mapping diagram, we have our input value 6 results in our output value 1. 7 results in one output value 7 and another output value 10. This is in violation of our definition of a function, given that there's two output values for one input value 7. Therefore, not a function. Now, let's say if the functions are represented as graphs, or the relations are represented as graphs. Are the how can we tell if the relation is if the graph is a relation or a function? In this case, we apply something called the vertical line test. So give it some space here. Vertical line test. In the vertical line test, we essentially draw one vertical line, or as many vertical lines actually, across our graphical representation and see if it intersects the graph at two different points. In this case, this is intersecting at one point, this is intersecting at only one point, this is intersecting as only one point, and this is intersecting at only one point. Therefore, this passes the vertical line test, and this graph represents a function. Now, let's dive into this more. Essentially, what the vertical line test is telling us is that by finding the intersections, we're finding different x values or different input values. So this is x1, x2, this would be x3, and this would be x4. And these are different input values, and they all correspond to one unique y value. So they only have one output value per input. And we're determining this by just simply crossing a vertical line across the graph and seeing if it intersects more than once. Now, so our first example does represent a function. In the second example, if we apply the vertical line test, we see that it intersects the graphical representation at 2 points. This is one x value resulting in two output values. So we could call this output value y1 and this output value y2. And again, a function has a single input for every single output. Therefore, this is in violation of our function definition and does not represent a function. So, no. The previous one was fine. Again, if we apply the same principle to our third graphical representation, we could see that if we cross the vertical lines across the graph, we only have one intersection per vertical line. Therefore, this, again, is a function. And then our last example, we apply the vertical line test, and we could easily see that every time we do so, we get two different intersections across the graph. So this is also not a function. I also wanted to point out that it doesn't have to always be the case, even if it's one part of the graphical representation that results in two intersections, it will still violate the it would still violate the vertical line test, and it would not be a function. So consider an example where we have a graphical representation such as this one. So it starts off here, and actually that was bad drawing. So it's something like this. Now, if we apply the vertical line test from at this side, there's only one intersection, it's fine. On this side, again, one intersection, it's fine. But if we apply it here, for this specific value, input value x1, and again, this is our xy coordinate system. So for this x1, we will get two y values. It doesn't matter that this part of the graph, it's fine. Even if there's one case in which the vertical line does not pass, the vertical line test does not pass, it violates our definition of a function. Therefore, this would not represent a function, not a function. Okay. And now, once we know that our function, our graph does represent a function, we could apply something called the horizontal line test. And essentially, the horizontal line test is a method that can be used to determine if a function is a one-to-one function. Now, for those of you who might not know, a function is one-to-one if no two elements in the domain correspond to the same element in the range. In other words, each x in the domain has exactly one image in the range, and no y in the range is the image of more than one x in the domain. So let's look at this more deeply. If we, again, similar to the vertical test line, we apply a horizontal line and determine where it intersects our graphical representation. We can see in the first example, we have two intersections, two different x values, therefore two different input values, results in one output value. So both x1 has only one output value, which is y1. x2 also has one output value, which is also y1. This is still a function. This does not violate our definition of a function because our input values only have one output value. It doesn't matter if that output value is repeated again in the future by another input value, but each input value only has one output value. Therefore, this is still a function. However, it's not a one-to-one function because for every y value in the function, there's not only one unique x value. So for y1, there's two x values. Therefore, this is not a one-to-one function, and that's fine. We have these in various mathematical models, and this is still considered to be a function. And then if we apply the same principle to the second graph, we could see that it also results in the similar situation. So we have 2 points here, again, two different x values, x1 and x2, but the same y value. Or here you have another, and here you have two more different x values, but again, they have the same y value. Again, this graph is also a function because the vertical line test, if you draw it anywhere in the graph, it still passes. There's no point in the graph where you could apply a vertical line and get two intersections with the graph. This is still a function, but not a one-to-one function. So still represents a function, but not a one-to-one function. And moving forward, we don't necessarily always have the luxury of checking the graphs or looking at different input values and output values to determine whether we have a relation or a function. Sometimes we are just given an algebraic representation and we'll have to determine using some algebra operations. Now, in the first example, we have x power 2 plus y power 2 equals 9. In this case, let's rewrite our relations in our general form. So we have y equals ax plus b. Let's write it like that. Again, our y is our dependent variable and our x is the independent variable. So if we rewrite this, we could say y squared. Sorry, I think I'm out of ink. So y squared equals 9 minus x squared. And if we want to get rid of the power, we take the square root of both sides, and therefore y would be equal to plus and minus square root of 9 minus x power 2. Now, as you can see here, whatever input value you put for x, so let's say you put input value 1, x, y, this would be 9 minus 1 would result in plus and minus square root of 8. Therefore, this violates our definition because for your input value 1, you get both plus square root of 8 and negative square root of 8. And those are two different numbers. Violates our definition of a function, which says that a function has a single input for a single output. This violates our definition, and therefore this relation is not a function. Now, on to our second example here. We have x squared minus 2y plus 49 equals 0. Again, let's rearrange this into our general form. Negative 2y would equal negative x squared minus 49. We're just moving the x squared and the 49 to the right-hand side of the equation. And we're going to do a division by minus 2 so that we have no coefficients for the y. So y will equal negative x squared minus 49 divided by negative 2. Now you could simplify this further and get rid of the minuses, but for our sake, it's fine. And you could easily see that per each input value x, we will have one unique output value y. That output value could be repeated in the future. That's a different story. That just tells us whether a function is 1-to-1 or not. But each input value x only has one output y. Therefore, this is a function. Our next example, x2 minus 2y squared plus 49, very similar to what we just did. Again, let's rearrange this in our general form. We'll get the same thing here, except this time we'll have y squared equals negative x squared minus 49 divided by negative 2. And again, if you don't know where I got this from, similar to our previous example, I just moved the negative x squared, the x squared and the 49 to the right-hand side, and I divided by 2 so to get rid of the coefficient. And the only additional step I'm going to take here is that I will get rid of the square root of, I'm going to get rid of the power of y, the power of 2, by taking the square root of both the left-hand side and the right-hand side. So y would equal the square root of negative x squared minus 49 divided by negative 2. And again, don't forget about the plus and minus when you take the square root of a variable. Therefore, in this case, each input value of x, each input value of x will have two output values, violating our definition of a function. Therefore, this is not a function. Again, very similar to what we had in the previous example, example number 2, the only difference is that the y has a power of 2, and that completely alters our results. So for every x value, per every input value that you place, you will get a positive y and a negative y. Therefore, this completely violates our definition of a function, and this is just simply a relation. For example number 4 and 5, I'm going to leave this to you guys to solve, and I want you to leave a comment below this video telling me whether they're a function or not, and explain your reasoning. Furthermore, if you want me to solve examples similar to what we did, either doing more examples on the equations, or doing more graphical analysis, or even looking at more sets and mapping diagrams, feel free to leave a comment down the video and I'll make additional videos solving more examples on this topic. Don't forget to like and subscribe, and stay tuned for future videos.